Well, good day to all of you. So, we have come to the second class of phase equilibrium thermodynamics. In the last class, I had given you a very brief introduction regarding system, surroundings, boundary and equilibrium state of a system, etc., etc. Now, when does a system deviate from equilibrium? As I told you in the last class, under normal circumstances, if any particular system is left to itself, it will not deviate from the equilibrium state, because it is most comfortable when it is in the equilibrium state. There are no driving forces and there is no incentive, there is no need for the system to change. A system changes only when it interacts with the surroundings by virtue of some sort of an energy interaction or a mass interaction, and when it is interacting, it undergoes a process. By virtue of this particular process, it shifts from one particular equilibrium state, it continues this particular path till it reaches a second equilibrium state, again when there are no unbalanced forces and it has no tendency or there is no tendency of the system to deviate from the second equilibrium state unless again it is forced to do so. So, therefore, the process which a system undergoes, it is defined as a method of operation in which specific quantities of heat, and rather it is better now we do not discuss about heat work, etc., in which a system interacts with the surrounding by virtue of some sort of energy interaction, as well as maybe there can be some mass interaction also, and during the process the system moves from one equilibrium stable state to another equilibrium state, and the succession of states which the system passes during this particular change, that is known as the path of the process. Now, let me tell you that usually whenever we undergo any particular process, it is quite fast, right, and it is very difficult for a system to remain in equilibrium during all the states it is undergoing when it is going from one equilibrium state to another equilibrium state. An idealized situation is a situation where a system, while undergoing a process, passes through a succession of equilibrium states. But this is an idealization, and often we assume that a system is actually passing through a succession of equilibrium states during the process, and we call such a process a reversible process. Now, let me remind you again, a reversible process is an idealization. It is never possible to we can try to attain a reversible process, but it is never possible to realize a reversible process in practice. Most processes are irreversible. If so, why are we so interested about reversible processes? We always try to rather simulate or model or rather analyze any particular process assuming it to be reversible, and then we find that, or rather we incorporate an efficiency factor to come to the actual energy interactions in the irreversible process. Why so? Why are irreversible processes which can never be realized in practice so very important? The reason is very simple. See, suppose we take up some particular amount of gas in a piston cylinder arrangement. A very conventional system which we will be dealing now and again in our course of thermodynamics, again possibly due to the history of thermodynamics originating from heat engines and heat cycles. So, for this particular system, in this case the gas which is contained in this particular cylinder, this is my system, right. And what I do, maybe this system, it is in contact with a thermal reservoir at a higher temperature, fine. So, under this condition what happens, some amount of energy flows from this particular reservoir into the system. When some amount of energy flows, suppose we can maintain the condition such that as the energy flows, we do not allow temperature rise of the system. On the contrary, the system keeps on expanding in volume and the piston keeps on going up very slowly, such that with entry of heat by an infinitesimal amount, which occurs when there is a dt difference of temperature between the thermal reservoir and the system, then the heat flow from the reservoir to the system occurs very slowly, and under that condition the system it expands at a very slow rate, and we find that with time the system gradually increases in volume by dV amount and its pressure reduces by minus dP amount, right. So, therefore, we can assume that at each and every state the system was in an equilibrium state. What does it imply? It implies that at each and every instant of time the system had one particular pressure value, one particular volume value. The volume value went on increasing very slowly, the pressure value went on decreasing very slowly, it is true, but for each particular state which the system was undergoing, from its initial position of the piston here to say the final position of the piston here, each and every state which the system was undergoing, it could be characterized by a unique set of properties, or in other words, the system was in an equilibrium state at each and every position. So, therefore, if we can plot the state of the system, say on a PV plot, maybe this is my initial state and say this is my final state. So, I know in this particular case I can actually plot the path of the process. So, therefore, in this particular case, when I can actually trace the path of the process, as we shall see after some time, it is very easy for us to identify the energy interactions which the system had with the surroundings during its entire path. It is given by the area under the curve. That will be, you also know possibly, and I will just discuss shortly. This area under the curves gives the energy interaction between the system and the surroundings. So, therefore, in order to calculate the energy interaction, it is very important to trace the path of the process. The path of the process can be traced only for a reversible process. So, therefore, a reversible process, although an idealization, it is very important. We try to simulate, or we try to idealize each particular process as a reversible process, where it comprises of a succession of equilibrium states with driving forces between the system and the surroundings being differential in magnitude, and this occurs for some two idealized situations like motion without a friction, no pressure difference between system and surroundings, or an infinitesimal pressure difference between system and surroundings, energy being transferred just like the piston cylinder arrangement which I have shown. Energy is being transferred with almost no temperature difference between the interacting systems, and so on and so forth. Now, well, there is one thing which I would like to mention, right. Now, what is the basic difference between a reversible and an irreversible process? When I ask this question in the class, the answer which I get is that on reversing the process, the system comes back to its original state, but this is not the correct answer. It can always happen even in a cyclic process also, that when we reverse the process, the system comes back to its original system. The important part is that the difference between reversible and irreversible processes are with the changes in the state of the surroundings. For an irreversible process, even when we reverse the process, the system might come back to its original state, but the surrounding is not going to come back. And for a reversible process, both the system as well as the surrounding comes back to its original state. Now, well, the most important part of my introductory lecture, why just as I have said, a system if left to itself, it remains in an equilibrium state. It changes in from one equilibrium state to another through a series of steps which comprise a process, etc., etc., and the process occurs only when there is some energy interaction between the system and the surrounding. Now, this word energy, you have been hearing about this word since your school days, and possibly in your physics book you have learned. Whenever I ask in the class what is energy, the answer which I receive almost every year is energy is the capacity to do work. Then my next question is what is work? So, therefore, these terms are very common, you have been using them since your childhood. Energy, work, process, system, all these words are very common. In fact, the entire concept of thermodynamics, it is based on common everyday experiences. We are dealing with very common words which you use in your everyday, but sadly that does not make the study of thermodynamics easier. On the other hand, it is always almost the contrary thing. So, therefore, in order to understand energy, the definition which I would prefer to give is energy is the capacity to induce a change in that which inherently resists a change. If you go through this particular definition carefully, what do you find? You find that it the word energy comprises of two parts. What are the two parts? First thing is that there is some particular force which is trying to induce a change in the system. The system is inherently resisting that particular change, and this particular force which is being applied, that particular force, it overcomes the resistance to change of the system, and then it performs the change in the direction of the applied force. The same thing that you have learnt in physics. In physics also you have learnt that energy or the work done that was equal to or say the work done that is equal to F into dl, sorry dw, it should be dw which is equal to F into dl, right. It is force into displacement. Just to keep a link or to keep a parity with that particular definition which you had come across, in this case also I define energy in this particular way, that it is a capacity to induce a change in a system which inherently resists the change. So, therefore, from this what do we see? We see that in that case energy, what does it become? In that case energy becomes a product of two terms. The first term is a thermodynamic driving force, which inherently overcomes the change which a system provides to resist a change, and once that change is overcome, then this particular driving force, it brings about a displacement of the system in the direction of the driving force. So, therefore, we find that just like physics, we find that we define energy as the product of two quantities. One is a thermodynamic driving force and the other is a thermodynamic displacement. The important part here is the thermodynamic driving force and the thermodynamic displacement, they are not defined in the same way as they are defined in physics. For our case, defining the thermodynamic, both these properties, the thermodynamic driving force and the thermodynamic displacement, both of them are thermodynamic properties of the system. Usually, what do we find? The thermodynamic driving force is an intensive property whose difference in magnitude between any two parts brings about a change in some other extensive property of the system which is known as thermodynamic displacement. So, basically energy in thermodynamics, it is a product of one intensive property whose difference in magnitude brings about a change in an extensive property of the system, and the driving force, it controls the extent and the direction of change in the thermodynamic displacement. For example, in the piston cylinder arrangement that we were discussing just now, in this particular case we found that some amount of energy was flowing, and due to this energy flow, it was expanding. And why was it expanding? Due to a pressure difference between the system and the surrounding. So, therefore, the pressure difference P, that was the thermodynamic driving force which was bringing about a change in the volume, which is the thermodynamic displacement. So, therefore, for the pressure volume type of work, we find that work done or the energy transfer, in this particular case, it is equal to integral of P dV, right. Now, one thing we need to remember in thermodynamics is that we can define the thermodynamic driving force and the thermodynamic displacement in any particular way, but when multiplied they should give you the unit of energy. For example, we can define, for example, what we can do is we can define the, for example, what we can do, say for example, we can define the thermodynamic driving force. Yeah. So, therefore, the thing is, it is very important for us to remember that whatever we are doing, the thermodynamic driving force and the thermodynamic displacements are simply properties of that particular system. One of them is an intensive properties, which is the thermodynamic driving force. The other one is an extensive property which changes, and that is a thermodynamic displacement. And the choice of these two, they are completely arbitrary. For example, in this piston cylinder arrangement, we could have very well assumed, instead of assuming this to be the driving force, we could have assumed the product of the pressure and the piston area, which is F as the driving force, and the displacement of the piston as the displacement. It hardly matters how we are going to define the, or rather how we are going to divide the energy into a thermodynamic driving force and a thermodynamic displacement. It is important to remember that no matter how we are dividing it, when we multiply the two, it should have a unit of energy. In this case, there is just one thing which I would like you to remember, that since thermodynamic driving force and thermodynamic displacements, they are scalar quantities. So, therefore, they are different from the displacement and driving force which we define in mechanics. For example, they do not obey the Newton's third law of mechanics, and it is important to remember that although these two are scalar quantities, but they are the collective property of a large number of the motion of the large number of ultimate particles which exhibit Newtonian mechanics, right. But since they are completely random, the average of all the displacements and driving forces of a large number of ultimate properties finally sum up to manifest as the pressure change which brings about the volume change. So, therefore, it is important for us to remember that in thermodynamics, we define energy as the product of a thermodynamic driving force, which is nothing but an intensive property change, and which brings about a change in any extensive property of a system, which is the thermodynamic displacement. Usually, since we deal with pressure volume type of work, so usually we define work done as integral P dV. Now, it is important for us to remember that the energy interactions between the system and the surroundings are usually in the form of work or in the form of heat, right. So, here I am not going to go into details. I assume that you already know it, or you can take it up as a home assignment. I have just found out what are the different expressions of the work for different processes, for different reversible processes, isobaric, isochoric, isothermal, adiabatic processes. You can very well take these derivations as your home assignment. In case you have any doubts, we can have the interactive session during your course, and the TAs will be very glad to solve any doubt that you have. There are other types of work also, which it is not only that PV type of work, we can have other type of systems other than a piston gas in a piston cylinder type of arrangement, but we find that for each particular system that you consider, we can break up the work done into a thermodynamic driving force and a thermodynamic displacement, and when we multiply the two, we get the unit of an energy. Right. Now, as I have already mentioned, there are two types of ways by which a system and a surrounding can interact or can exchange energy. It can be either in the form of a work or in the form of the heat. For both of them, we need a thermodynamic driving force and a thermodynamic displacement. When the driving force is the temperature difference, then we call that particular energy interaction as heat. When the driving force is anything other than the temperature difference, we call it as the work. Now, here I would like to mention one thing. Since we are dealing with properties, so therefore, this driving force and the displacement, both of them can be the property of a system, both of them can be the property of the surrounding, or else one of them can be the property of the system, the other of the surroundings. For example, suppose I take up this particular arrangement. I arrange my system such that my system comprises of not only the air in the piston cylinder arrangement, but also some portion of the surroundings as well. Now, in this particular case, we find that the pressure difference which was bringing about the volume difference, everything was a property of the system. So, therefore, the energy change which took place here is also a property of the system. Similarly, suppose I define my system somewhere outside such that this whole thing is a property or it lies in the surrounding. Then in that case, we find that the energy interaction was a property of the surrounding. But suppose I have my system as the gas contained in the piston cylinder arrangement, then we find that maybe not this case, a better case is when work is done. In this case, what happens? Suppose I apply or I gradually increase the pressure here, I find that the piston, it keeps on coming down and it compresses the gas. So, in this particular case, what happens? The pressure which is applied, that is a property of the surrounding, and the contraction or the compression of the gas or the volume decrease of the gas is this particular volume is a property of the system. So, therefore, for this case, the energy interaction which occurs, whose property should it be? Because in this case, actually the energy interaction is occurring across the boundary, which is a zero thickness interface between the system and the surroundings, and the energy interaction occurs because there is the pressure of the surrounding forces a volume change inside the system. Under this condition, we say that it is energy in transit. It is neither a property of the system nor a property of the surrounding. It is a path function. It is energy in transit, and as a result of which we consider this type of energy in transit as path functions whose differentials are inexact, due to which we are going to represent heat and work interactions between the system and the surroundings by means of a different sort of a differential as compared to the exact differential by which we had depicted a property. This is something very important which I will be following in the class. I would want you people also to follow this, that we would like to differentiate between inexact differentials and exact differentials. The path functions will be shown by inexact differentials and the state functions will be shown by exact differentials. Now, in this case, so therefore, I would like to mention that heat and work, they are quite unique. Why? Because they are the energy interactions between a closed system and the surroundings, and we can have the same effect both by heat as well as by work. For example, in this particular case, the expansion of the system could have been brought about by pressure changes in the surroundings, in which case we say that work is being done, this case, in which case we say that work is being done on the system. We can also bring about the same change by a temperature differential with the surrounding, in which case we say that heat is being transferred to the system. If you observe the initial and final state in this case and this case, we find that they are the same, but the change in this case was brought about due to work done on the work done by the system from the surrounding, and in this case it was due to the heat transfer between the system and the surroundings. Right. Now, you have to remember that before the change and after the change is over, we just see the change of state. We see the initial volume of the system, the initial temperature, the temperature and pressure of the system. We see the final volume and the final temperature and pressure of the system. We are in no position to understand how this change has been brought about once the change is completed. So, therefore, we can just see the change which has brought about. So, therefore, it is very important to remember that heat and work have meaning as long as the change is going on. Once the change is over, we find a change in the property of the system. We do not know how that change has been brought about. So, therefore, please remember there is no total heat or work content of the system. There is a total energy content of the system, but there cannot be any heat or work content of the system. They are just manifested as long as the process is going on, and then they are manifested once the process is over by a change in property of the system, which shows that there was an energy interaction between the system and the surroundings. It does in no way show that there has been, or in what particular form that energy interaction had taken place. Now, before I end, I would give you a very interesting example of how the choice of system dictates whether it is work done or it is heat transferred. During winter, every day we heat up our water in our hostels by using an immersion heater. Most of us, we have immersion heaters which we dip in the bucket of water and we heat the water. Now, suppose we assume that our system is just the water in the bucket and nothing else. Then in that case, how does the water get heated up? There is a temperature difference between the rod of the immersion heater and the water, due to which energy gets transferred, and it is heat transfer which heats up the water. Now, suppose you think that, well, no, the water is not going to be my system. My system is the entire thing inside the bucket. That means the immersion heater, the water, everything contained in the bucket. In this case, how does the water get heated up? It gets heated up because of the electrical work which is being done on the rod by the battery. So, therefore, in this case, it is work done on the system. So, it is important to remember why I was emphasizing so much on the choice of system. The choice of system is very important because that decides whether we are having heat interaction or work interaction. As we proceed, you will find that the choice of system may make your calculations difficult, or it may make your calculations easier as well. So, therefore, choice of this system is very important, and before I end, I would like to discuss the sign convention which we are going to use for my work and heat in the entire course of phase equilibrium thermodynamics. The sign convention is that when heat enters a system, it is positive, and when system does work on the surrounding, it is positive. So, therefore, we follow this sign convention and proceed for our next class. Thank you very much.